We'll go ahead and start the recording. All right. How many of you guys actually got to watch the live that I recorded and posted yesterday for you? Thank you, Pilar. I appreciate it. All right. Well, I'm sure you'll be able to find good. Amy, did it help you any? We'll be using some of those, good. We'll be using some of those same drawings today, those images today. I went ahead and took me 2 tries to record it because I didn't bother taking myself off mute the first time. So it just was about 20 plus minutes of just images and no audio. It was great. But anyways, the second one was better, I think. Anyways, it had some audio on it. So what we're going to do now today is good, thank you. Good morning, Emily. What we're going to do today is we're going to hopefully be able to build on that, and that's why I went ahead and posted it in advance, just to kind of give you just a highlight moving into it. Just put out some of the information and talk about some of it, so that when we talked about it today, it maybe had a little more of a chance to sink in and help you, and today maybe start to become more where you're owning that information this time around. I know you got to go through interactions with Miss Menzel. You got to go through them again with Dr. Wyatt. So, maybe 3rd time, 4 times the charm. Don't know, but, at least you get to hear about them from different perspectives. And I always think that's helpful because none of us approach the physics in the same way. Ms. Menzel, because she starts off at the very foundational level, she always brings stuff in and is very strong on giving you that book knowledge and getting you to recognize specific things about the interactions. Dr. Wyatt has an approach all her own. My approach to physics in general is more a real world approach to physics, because physics explains why everything that happens in the world. It explains why when I turn on the light switch, I have current and I get a light. It explains why power fluctuates, so that light sometimes can dim in your room and brighten, and it explains everything that's happening in our universe. So I'm very passionate about physics. I love physics because I love sciences that explain why things happen, because I happen to be a why person. I always want to know the why behind something, so I never mind students who want to know the why. So anyways, with that being said, we'll go ahead and we'll start talking about the interactions, but before we start talking about them, we'll start with tube interactions, because without the tube interactions, we wouldn't have X-ray photons. So then we wouldn't even have to worry about X-rays interacting with matter, because we wouldn't have any. So at the tube level, what we have is we have kinetic energy in the form of the projectile electron that is being forced across the tube at half the speed of light. I mean, my mind can't even comprehend that speed. I wish I could run that speed, but no, I cannot. But so half the speed of light, it's charging, being sent across the tube. It's only less than a couple centimeters really across, and it smashes into the target, and it will either be converted to either thermal energy in the form of infrared radiation, which is heat, and that's the predominant interaction that does occur, because we know with all the interactions with the target that the majority of them produced heat. And by the majority, I mean like 99% of the interactions that occur produce heat. So heat's always a huge problem for us in the X-ray tube, and we have to spend a lot of time and energy in developing the X-ray tube is spent in ways to dissipate that heat. So it has to be done for us. We have to be concerned with it as technologists to not overheat the tube, although nowadays most rooms are kind of more smart rooms or dummy-proof rooms, however you want to look at it, because they won't let us overheat that tube. They'll stop us from being able to expose. So which is different than it was, back, 1,000 years ago when I, was in X-ray in the beginning of time, back with the dinosaurs. And so it is different, but the heat is a problem for us, whereas obviously what we want the tube to produce is that electromagnetic energy in the form of X-rays, and they would be either BREMS or characteristic, and it would depend on the energy or the kV of those particular projectile electrons, whether or not there was enough energy there or too much energy there to produce any characteristic X-rays. So we know we'll always have BREMS. That's a given, because BREMS is not energy dependent. As long as we have projectile electrons going across that tube and interacting with the target, we are going to produce some BREMS X-rays. Characteristic, unless I have a specific energy level that is reached, and it has to be right at that level, because once it goes too high or it's below that level, we won't have any characteristic X-rays being produced. And those characteristic X-rays are based on the K-shell binding energies of the target atom. So our target atom that we're talking about is obviously tungsten for us in X-ray. And again, we know we have different types of targets. We have a molybdenum target that's used in MAMO. So depending on what that target material is, it will cause a change in the characteristic energy, the energy that it takes to create those characteristic photons. So when we say characteristic is energy dependent, it only occurs at a specific energy, so it affects that discrete portion of the curve. So we have a BREMS, which is a bell. And let's see, you guys know I can't draw good, but I'll give it a shot. Let's see. First, I'll just try to draw my graph there. Whoo, I managed to get almost straight lines. Okay, so BREMS is going to look more like this. Okay, it's going to be a bell-shaped curve. All right, so anytime you see BREMS, you're going to see that emission spectrum as a bell-shaped curve. Okay, and that's because BREMS happens at any energy level. We know energy is the x-axis, so it's the horizontal axis, and y-axis is the vertical axis, and that's the number of. Okay, so when we talk about characteristic occurring, I'm going to say characteristic line here, because that won't occur until, let's see, I'm just going to type it in because I can't write good with that little pencil. That's real big, but you get to see it. So it would have to hit that energy level before we saw any characteristic occurring. So continuous, discrete. Okay, if I use my pointer, continuous and discrete. Everybody okay with this info so far? Okay, good, good. Okay, so those two interactions, again, those are the ones that are that projectile electron interacting with the target material. So BREMS, the more projectile electrons I send across, so that is your tube current, right? So the higher that tube current is, the more BREMS X-rays I would have, okay, and the more heat. So keep those two things in mind because the heat's always going up with the tube current going up. So the more projectile electrons I have, the more BREMS I'll have. Characteristic, I have to hit that specific energy level and have projectile electrons that have that, say, 70 kV of energy so that they have to have slightly more energy so they can knock that inner shell electron out. So they have to have slightly more energy than is the binding energy of that K shell. So, and BREMS, again, we're talking, a nuclear attraction. So we'll get into more detail with that. I'm going to flip back to this in a little bit. I kind of just wanted a little bit of a synopsis of information for you guys. So I put that together. And then I did my images. So. And of course, you guys know I can't draw, so what can I do? I can sure as heck search the internet and get good information to pop on there, and lots of people can provide better drawings than I can. Okay, so what we're looking at here is we're looking at the BREMS, and if you watched my little pre-session yesterday, you got to see this information as well. So what we're talking about is here's our incoming projectile electron. If it comes and it passes very close to the nucleus, it is heavily influenced by the magnetism of the nucleus because opposites attract, right? So if it passes really close, it will give off a lot of energy, and it gives off that energy as a high energy BREMS X-ray photon. If it just passes, kind of close, la-dee-dee-dee-da, walking along, it's not heavily influenced by the nucleus, it's going to give off just a little of its energy because it's not going to have that breaking occurring. So this would result in a low energy BREMS X-ray photon. So the closer it passes to the nucleus, the more it feels the attraction of the nuclear force field, the more energy it'll give off. So I gave you an example yesterday and said, like here, we're looking at, say we had a projectile electron that energy was 100 kV, and it going around, it passed very close to the nucleus, so it gave off a ton of its energy in a BREMS X-ray photon, and when it exited, it only had 30 kV energy left. So that would mean the 100 minus the 30, that this BREMS X-ray photon would have a 70 kV BREMS photon, X-ray photon. So this one, say it started off at the 100 as a projectile electron. it passed by the nucleus, wasn't very attracted to it. It came out the other side, and say it had 80 kV of energy left. And that would mean that this REMS X-ray photon would only be a 20 kV X-ray photon. So that's the difference in how we would have, and so BREMS, again, those BREMS X-ray photons happen all across the energy range, and their energies that they represent will be across that entire spectrum as well. Everybody okay with that so far? Okay. The most important thing about BREMS is that no matter what, at anything, say up to that 69 is all going to be BREMS, 100% BREMS X-rays. And then once we pass that threshold, and usually the only other option that the registry gives you is like at 100 kVp, and at 100 kVp it says that 85% of that X-ray beam is BREMS X-rays. Okay, so those are just two numbers that you'd want to be aware of. So if I picked 55 kVp, you would tell me that all the X-rays that were produced in that beam were BREMS X-rays. Everybody okay with that? All right. Okay, so here all I did was gave you, and if you watched that yesterday, you've seen these images. I just gave you a side-by-side comparison because, you know, Miss Ray can't draw. So just showing you that passing, you know, it passes by the nucleus, and it's just slightly affected. You see, it just has a little bend there, and we're talking about a low energy X-ray that is being produced. The more it passes closely by and stay closer to it, the more it would give off a higher energy BREMS X-ray photon. Okay, so characteristic, again, we know characteristic is only going to happen at a specific level, and we know that K characteristic X-rays are the only useful characteristic X-rays for us within the diagnostic range. And so what we're talking about here is we have that incoming projectile electron hitting an inner shell electron of the target atom, so our K shell electron, the target atom, and we know it can hit an L shell. L shell has a lower binding energy, so it's easier for that one to get knocked out. So you just have to pay attention to this, but K shell's the only one that's useful to us. So it comes in, it interacts, it knocks this out, it's out of that atom. The projectile electron can, goes on to interact with something else maybe. So then what has to happen is these electrons from shells that are further out will drop down and fill that void left by the electron. So if it came down from L shell and dropped into the K, then something from M could come in and fill the void in the L shell. So that's our characteristic cascade. So when that occurs, what happens is that going down, filling that shell provides us with our X-ray photon. And like I said, the K characteristic, so this little one here, this one would be the only useful X-ray photon for us, because L is going to be somewhere between 12 and 17 kV. That doesn't sound like an X-ray photon we're interested in, right? Too low energy. So the K characteristic depending on the binding energy of the shell that it dropped down from to fill that void, could be either 57, it could be 66, or it could be 68 keV X-ray photon that's been produced. Okay? Is everybody okay with that? Did you understand? Because I went through it yesterday how I get those numbers, and it's in Bouchon. It's the difference in the binding energy between the K shell and the shell of the electron that dropped in to fill its binding energy. As long as everybody's okay with that. And again, this just shows that this interaction without the background, so I thought it was a little easier to see, so I'll put it back up there so you could see it. And again, there's our characteristic X-rays being emitted there. And again, just that's the end of, so all those two, BREMS and characteristic, that's how we get X-rays, okay? So that's a projectile electron's interaction with the target atom producing an X-ray photon. Now we're going to deal with what happens with that X-ray once it exits the tube. So now I not only I have that X-ray photon, so whether it was BREMS or characteristic isn't going to matter to us anymore at this point. It is just an X-ray photon at this point. So now within the diagnostic range, when we talk about the interactions outside the tube and with matter, what we're talking about is it would either be photoelectric interaction or Compton. Those are the two predominant interactions within the diagnostic range. The only other thing that could happen would be transmission, which transmission is the X-ray going through the matter without any interactions. So, and we know that X-rays can interact with matter multiple times. So, and that would be, if it was interacting multiple times, it would generally be through scattering, because we know that once we have that photoelectric interaction, that's the complete absorption of that X-ray photon. Okay, so within the diagnostic range, what we're talking about is an X-ray photon interacting matter either through photoelectric or through Compton. So, first interaction that we have here is our photoelectric. And if you happen to notice, this photoelectric looks, I want to pop back to it so you can see, this photoelectric looks a whole lot like characteristic. Okay, just want you to pay attention to that. Looks a whole lot like it. First of all, we have an X-ray coming in this time instead of a projectile electron. That's why we know it has to be photoelectric, because I have an X-ray interacting with an atom. Okay, so here's the X-ray coming in. It hits the inner shell. It ejects that electron. That electron is called a photoelectron. Then we have, what we had before. We have cascade effect occurring where electrons from shells that are further out fall and fill the void. Okay, so they come in and they fill the void that was left in the K shell, and then this one fills the void that was left in the L shell. And what if we produce? We produce some characteristic radiation. Now, keep in mind, this is happening inside a human body, okay, for the most part, because that's what we're talking about, the X-rays interacting with. We know they could interact with other materials, but we're concerned with what happens in the human body. So there's this secondary radiation that's being produced, and it is characteristic radiation. So we don't worry too much about it. It gets absorbed almost immediately. But again, it's another interaction that's occurring. And as long as interactions are occurring within the body, damage can be occurring. So the damage caused by X-ray, it's not only caused right at that exact moment of exposure. The time for damage is extended until all the atoms that were interacted with reach stability again. That's why there's that concern about the damage from X-ray. Is everybody okay with that so far? I'm taking that as an okay. All right. Okay, any questions about any of this so far? We're feeling okay. Okay. All right. So now here, I just have a side-by-side comparison or above-below comparison of photoelectric and Compton. Because again, these are the two interactions that are happening inside the patient. We want to be aware of them. So photoelectric, again, inner shell interaction. Okay, X-ray photon coming in, knocking out an inner shell. It doesn't specifically have to be a K, it just has to be an inner shell. Okay, so it could be a K, an L, doesn't really matter. It's just an inner shell. That X-ray photon gets completely absorbed. So in photoelectric, the most important thing is photoelectric is responsible for patient dose. So when we're doing extremity work, and that's kind of changed over time, but especially with film screen, when we were doing extremity work, we're always talking about X-ray absorption, and bone absorbs more X-ray because it's a higher atomic number. As far as the different tissues in the body, bone has a very high atomic number, so it's always going to absorb more X-rays in soft tissue and so on and so forth. So it's important to recognize that bone will do the majority of absorption of X-rays. So when we're doing extremity work, we're talking about higher levels of the absorption occurring, okay, because of the amount of bone. So photoelectric inner shell, again, we have that secondary radiation that's being produced, and we're talking about the absorption by that atom of the X-rays energy. Okay, and again, we have the byproduct, the photoelectron, and the secondary radiation. Compton. Compton is X-ray interacting with the outer shell. Okay, so it doesn't, as we know, as we get farther from, as the shells get farther from the nucleus, they have less binding energy. So they're not held as tightly the further out we get. Closest to the nucleus, the most binding energy. The farther, the least binding energy, but higher potential energy, which is important. So we have this X-ray photon coming in. It knocks out this outer shell electron. That's referred to as a recoil electron. And then we have a scattered X-ray or Compton scattered photon here. So, and the important thing here is that scatter can go in any direction. So obviously, two things that we want to avoid. We want to avoid that scatter reaching our image because it only results in negative contribution. So we don't want it to hit our image, and we don't want it to hit us, because Compton's responsible for occupational exposure. It's responsible for our dose out in field. So we try to do things like, I don't know, not stay in the room. We need to be far enough from the patient to not be affected by Compton. We want to wear lead to attenuate the Compton scattered photons that could affect us. So there's all these things that we do, our cardinal principles, right? Time, spend as little time in the room as possible. Distance, give ourselves, we want to have at least 6 feet. So standing behind the shield, our barrier, in being in the control booth, and wearing lead. Those are all things that we do to protect ourselves from Compton, because Comptons are our problem for us. So again, this is just showing the Compton occurring here, knocking out the electron, and then the Compton scattered photon. And again, biggest deal is that it can travel in any direction. It basically retains, that Compton scattered photon retains about 2/3 of its energy from each scattering event. So it generally, what we say is it takes 2 scattering events before that Compton scattered photon is no longer an issue for us. So up to that point, it's still a problem. Okay. Everybody okay on photoelectric and Compton so far? Okay. So those are the main interactions. Those are the ones that if they're asking you about something in the diagnostic range that you have to pay attention to, those should be your 4 go-to answers. So when I told you and I was describing photoelectric and I said, look, it looks like the same thing as what's happening in the tube with characteristic. So a lot of people can mistake one for the other. What you have to pay attention to is, one is a projectile electron's interaction with an atom. That means it's happening in the tube. I don't have an X-ray photon yet, okay? The second one is happening inside a patient. That is an X-rays interaction with the target atom. So that's happening inside the patient. So that one now is an X-ray. That has to be photoelectric. If it's giving you, okay, it produces, characteristic radiation, blah, blah. If it's happening inside the patient and it's an X-ray photons interaction with, that means now it's photoelectric versus characteristic. So you have to be able to distinguish those two. And Compton's always going to be an X-ray photons interaction with matter. So I'm gonna flip for a second here and see if I can't. Nope. Too bad. I knew that was going to happen. I was going to lose that info. Blackboard's not always our friend. Sorry, guys. Just trying to go back to show you something that I don't get to. So when we're talking about those two, you just have to be able to distinguish them and pay attention. Are we talking about an X-ray interaction with, or a projectile electrons interaction with? Okay, so things that really don't matter to us, but that you have to be able to recognize for testing purposes and for your registry. Okay, so these last 3 interactions are all not in the diagnostic range. They're either above or below. So as X-ray technologists, they don't matter to us except for in testing situations where we have to be able to pick or eliminate them. So any of these interactions will be described to you. If they're not specifically described to you, then you can toss out those as answers. Okay, so they're just throwaways. So below the diagnostic range, we only have one. We have coherent. It happens below 10 keV. So when we say that coherent is negligible as an interaction in the human body, that's correct, because generally once we get to that 10 keV level, that that X-ray will have already have been absorbed. So it's just to recognize that. So coherent is non-ionizing. So again, because that energy level is so low, there's no ionization going on. It is just a vibration or excitation. All it does is result in a change of direction with that X-ray photon, and the X-ray photon's energy remains the same. You have multiple names that are given to coherent scattering. It can be referred to as it is here, classical scattering, coherent scattering, unmodified. Think it doesn't get changed, so unmodified. Thomson, Rayleigh, these are two different people who discovered the coherent scattering. And again, all it results in is a change in direction without any change in energy. So no energy is given off to the atom that it's interacting with. And that's the only one that's below the diagnostic range. So the next one is one that's occurring above the diagnostic range. So while this isn't important to us in diagnostic imaging, it is important in radiation therapy. So may not be important to us, but if any of you guys go on and decide to go into radiation therapy, then you're going to learn a lot more about this than we'll deal with right now. Right now, we'll deal with either being able to choose it for an answer or eliminating it. Okay, so I have to have an energy of at least 1.02 MeV, MeV. We deal with KeV, right? So MeV, mega electron volts, much higher range than we're dealing with. This is considered an annihilation interaction. And what's happening is that positron unites with a free electron, and the mass of both of those particles is converted to energy. Okay, so that's that matter to antimatter. Okay, the two byproducts, the positron and the negatron, split the energy. So whatever that energy was, so if we started off with that 1.02 MeV, then the positron and the electron would each have either 511 keV, or if we're listing it in MeV, it will be 0.51 MeV of energy each. Okay, that's pair production for you. I just love the drawings. I thought they were so cute. So photodisintegration, it sounds scary, right? It actually is pretty scary, I think. So photodisintegration needs an energy level of 10 MeV or more. So super, super, super high energy. The interaction at that level is with the nucleus. So this X-ray comes crashing into the nucleus, and in order for that nucleus to remain stable, it immediately ejects a nuclear fragment. That nuclear fragment can be a proton, a neutron, neutrino. This is where we can get some of that alpha decay occurring. So that's what's happening there. To me, that sounds like so scary to me. Maybe they can explain to me why it's not that scary, but I'm like, oh, if we got parts of the nucleus being ejected, that doesn't sound real cool. But that nucleus at that point is trying to regain stability. So that's why that that portion of the nucleus and the nuclear particles are being ejected. So those are the things that we want to recognize about those interactions. So if they are not specifically described for you, then you automatically know, eliminate those as answers. Photo disintegration happens to be important in PET. So, and you'll learn more about that when you come back from your clinicals and you have your advanced modality class with Dr. Wyatt, and you'll deal with the different modalities, and also you'll see PET scanning, and it's important in PET scan. So, but for us in diagnostic range, there's no relevance to us. Okay, so questions at this point? Okay. Wow, I didn't make you question anything. I'm amazed. Okay. I wish my pen would not have wiped out my whiteboard, because that would have been nice. So some of the last things that I want to talk about when we talk about, let's go back to talking about our X-ray interactions that are occurring inside the patient. So either photoelectric or Compton, right? So when we talk about those two and we think about attenuation, when we say attenuation, the exact definition for attenuation is the reduction in numbers of X-ray photons as they travel through matter. Okay, so obviously we tend to be talking about the patient, right? And so how would that attenuation be occurring? That attenuation is occurring through a combination of photoelectric absorption, so the X-rays that are being absorbed within the patient. So we know things that cause us to have more photoelectric absorption. We know that the higher atomic number of bone, the higher the atomic number is, the more photoelectric we're going to have. So bone's going to absorb more. We use contrast agents, what we consider to be positive contrast agents, barium, iodine, and the like, to cause more photoelectric interaction. So anytime we're using a positive contrast agent, we are causing more photoelectric, so more attenuation to occur through photoelectric interaction. And we know that we're going to reduce the number of X-ray photons by Compton interaction as well. So a combination of absorption and scattering results in that X-ray beam being attenuated as it's moving through the patient. What we're left with at the end of the day is we may be left with some Compton scattered photons. That's a negative, okay? That's not good. We would rather have no Compton coming out of the patient. But we do, and it can interact with the imaging plate. That's always going to be a negative. Transmitted X-rays, ones that go through the patient without interacting in the patient, they'll just interact with the imaging plate. and that would be responsible for the black areas of the image. So that's interacting with the X-ray plate, and then that's considered remnant X-rays, what's left after the beam has been attenuated. Transmission can occur with radiolucent materials, and any atoms that have a lower mass density than others. So obviously, if it has a high mass density, we look at having more photoelectric and more Compton interactions occurring. In between those two, the photoelectric represents on the imaging plate represents an absence of information, and Compton represents negative information. So what we're saying is it doesn't contribute anything useful to the image. Compton doesn't. It doesn't give us any useful information on our image, whereas photoelectric is responsible for information on the image by a lack of interaction with the IR, because those X-ray photons didn't make it through to interact with the IR, so they would be represented by white or clear areas on the image. Does that make sense? Okay. All right. So again, photoelectric, all about patient dose. The more photoelectric interaction we have occurring, the higher that patient's dose will be to that body part. Compton is what we try to avoid. And again, that's why the cardinal principles are established of time, distance, and shielding. That's to protect us as technologists from having radiation exposure, unwanted radiation exposure. As we know, there are times when we absolutely will have radiation exposure and it can't be avoided. So all those times when we actually can avoid it, that's what we're trying to do. Okay, so I can't think of anything else really that I wanted to say. Like I've been yammering for quite a while. Is there anything on any of these images that you'd like me to go back over? Is there anything that you feel like you have a question about that maybe I didn't hit on or I didn't talk about, and so there's still some confusion for you? Okay, well, I guess if everybody is okay, boy, I must be a genius. No, just kidding. If everybody's okay, then I'll go ahead and let you go at this point. Remember, tomorrow morning, you're going to come into campus at your designated time to meet with Ms. Stevenson to get your clinical notebooks. And if I don't know if you have any information you have left to give her or whatever, but if you have something that's required for you to bring in, make sure you bring it in. And then there's a couple of you that I expect to see before your time with Miss Stevenson. So get with me. I will be on campus, and I'll also be there so that you can get your workbooks to me. So that should pretty much be everybody, because everybody should at least be showing me that they have their self-tests finished. I don't think, I think that everybody at least owes me self-tests. So make sure you get with me and show me those tomorrow, either before or after your time with Miss Stevenson. If you're in the second group, I don't know that I'll be there until the end of your time, but I plan on being there. I'm sure I'll be there before 9, but I'm thinking of being there between like 9 and 11. So 11-ish is probably when I'll be considering going back off campus to get stuff done. So just make sure you get in and see me with your workbook. That's what I need from you. And then other than that, make sure you get rad reviews into me before your final on Friday. Okay? All right. Well, at this point, I guess I will say goodbye to you. You're welcome, Pilar. You're welcome, Katie. All right. And I'll see you guys tomorrow. Take care. Get a lot of work done this afternoon. Get ready for your final.